Right. Got a few more minutes. So pretty much as per, I'm just going to shut the door like mostly the way when when about 7, just because otherwise we've got K-bar. So that's for when you're taking your notes down.
Yeah, that's what I was asking if you had a clicker.
Nah, I don't.
Good point.
I extensively just label everything, so I don't like that to be time wasted. Um, well, I can answer the majority of the questions of where are you, when will you be here, what room is it in. Yeah, Keynes is a nightmare. I got LT6 for one of my maths lectures, and I was like, oh no, that's fine. I go to LT5 all the time, and I was expecting it to just be like the one there or whatever, but it isn't. It's like all the way back there. I mean, we'll just see how the thing works out. This is mainly a trial run. As long as you're getting a couple of pictures, then we just have that to thing. Okay. Sasha on his way?
Yeah, he says
That's normal. Every time I have that issue, I'm like, I've got to predict it by like an hour before.
20 quid says he's still
That's true.
Yeah, that's so true. It's actually probably in one of my lectures. Do you know what's even more unstable? Southern trains.
Yeah.
It's like, oh yeah, no, my train's a minute early. No, it's actually 59 minutes late. Yeah, it does take a lot of effort to make a business model look like quantum mechanics. They are trying. They're doing a pretty good job of it, to be fair.
We got some high quality karaoke downstairs. Yeah, you can hear it. It's not shot, it's just it's a bit more custom.
Right, well, hello everyone, and thank you for being here. Nice to see quite a few familiar faces. Now, obviously, same routine. I'll have a few bullet points, basically just to keep track on my phone, so I don't go on for hours about something that interests me a little bit more. I just want to make it plain that for a lot of the images and data in it that I obviously take no credit for, that there are some bits that are findings that I manipulate in a certain way for this presentation, but beyond that, it's mainly data that is sourced elsewhere. For this talk, because we are going to do some publicity stuff, there will be the camera recording, just me, and then sound recording, so potentially if you do ask a question, your voice might get recorded at that. If there's any issues with that, we can easily clip it out, but just letting everyone know up front. So this talk is on the solar system, and it will basically take you from the birth of the sun, and therefore the birth of the early solar system, through every event of note that actually happened to get to where we are now, and all of the events that are unfolding right now. For understanding this journey, there's a key unit which comes up quite a lot, which is the astronomical unit. So the astronomical unit is the average distance between Earth and the Sun. It is around about 150 million kilometres. But because the distances are so large in the solar system, it's easier to say one astronomical unit than pretty much any measurement. So, for over 100 years, our solar system was presumed to be normal. We looked out into space expecting to find very similar structures to what we have to look at directly, and that sort of makes sense thinking about it on the surface. If we're here and it's here, chances are everything else is probably like it. But the key difference is it's actually our solar system that is extremely weird. There are a lot of characteristics of our solar system which are really not that common at all. One is the layout of the planets and how many fall into roughly circular orbits. And then another one is the sheer density of massive planets that haven't come together to be one thing. Some of the planets in our solar system are so extreme, not necessarily seeming weird to us, but there are planets in our solar system that we have never found anything like in any of the 6,000 or so confirmed planets in every other star system. Some of them are quite interesting because they are commonly the ones that are overlooked, the ones that we see as boring or insignificant. Obviously, the story of the solar system is tied intrinsically to the sun. So, to go back to the beginning, first have to ask, where did the sun come from? Obviously, anyone who was here for my last lecture. So, stars basically form in massive clusters of gas that can be 1,000 odd light years wide. This gas and dust is intrinsically unstable purely because it's not spread evenly across space. It's warped by other bodies orbiting near it, and it's also unevenly distributed from past events like supernovae and other forms of dead stars. This makes it ideal for undergoing gravitational collapses. Each pocket of that gas and dust can basically break away and cool on its own. It's called fractaling. And once that cloud becomes that fractal pattern, each pocket is like an isolated seed for a solar system to form. All it needs is a trigger. That trigger, in our sun's case, was a nearby supernova. So the supernova exploded and put out basically a blast wave through the cluster of gas that would become our sun, giving it angular momentum. It's where the spin of the solar system originates from. Alongside kicking up the dust, it also seeded the cloud with heavy elements that weren't in it before. everything from gold and lead to some more extreme stuff like europium. The actual point that focuses in on once the gas cloud starts spinning basically becomes shrouded in a sphere of heated dust and gas. That undergoes even more gravitational collapses and basically creates this stable, very hot centre shrouded by an envelope of gas, and that's called a protostar. So that's what that image is showing there. Now, that protostar isn't a star yet, purely because it doesn't undergo one of the key things to make a star, fusion. What it does instead is start spiralling in great plumes of dust and gas from its accretion disk that then fall onto the star and build up its mass and temperature at the same time. Once it reaches around the mass of about 13 Jupiters, it can start undergoing the first form of fusion, which is deuterium fusion, a heavy isotope of hydrogen. At that point, it's considered a T Tauri star, and that's where the birth of the solar system as a system of planets begins. Once the T Tauri star forms, it can start pushing away lighter elements of the dust and the gas from the inner solar system and thin out the disk a bit, which allows it to cool. And it's only once that disk can actually cool below about 400, 300 Kelvin, 300 degrees, that planets can actually start forming their building blocks. This is a process called accretion. And the key focus of the inner solar system is core accretion. It's where molecules of mainly silicates and iron and heavier metals and all of the things that make up the rock on a planet basically merge together slowly after forming small crystalline structures. Once they grow past a certain size by chance encounters, they can start runaway accreting. That means their gravity is attracting nearby other pockets of basically grains of sand and things like that to build up the actual structure of what will become the planetary embryos. This process of planetary formation only has a window of 10 million years. That T Tauri stage is the only time a star system can ever form a planet. If a planet doesn't form in that window, which is a really short time on the universal scale at least, then it will never form. That's why there is quite a high abundance of very hot birth clusters such as this, having their gas dispelled over a very short region of time by nearby recently birthed stars that will then end up having no planets at all. The first planets are essentially made up of those very basic building blocks. By about 1 million years in, everything in the protoplanetary disk is cooled enough to start condensing into clouds of rocks around 1 kilometre wide. That's when the rate of accretion really picks up. Once they can smash into each other with the force of 1 kilometre wide piece of rock, you end up having them generating heat and merging on a larger scale. Each body that gains more mass becomes more likely to accrete more, and this is a building process that massively favours larger bodies. Towards the end of this early planet-forming era, you have objects like this, which is a planetary embryo. They tend to be around 1,000 kilometres in diameter, so the size of a large moon. But it's these objects that formed the bulk of stuff on the inner solar system for the first 5-10 million years of its life. Once the sun moves out of that T Tauri phase, the reason why the planetary window goes away is because at the end of that phase, it's hot enough and massive enough to start fusing hydrogen, which generates a lot more energy. That's when the star steps up into its current phase, which is called its spectral phase, or its main sequence. In our case, because of our sun's mass, it made it a class G star, a yellow star. Once that type of fusion ignites in the core, it basically creates a shock wave of much faster particles with a lot more energy. That's called solar wind. And the solar wind, how it actually originates at such speed from the photosphere is actually a little bit of a mystery. But the thing that we do know is, because a star gives off so much energy in the form of solar wind, it can generate enough force to push out even planets that are forming close to a star, let alone the dust and gas that would be left behind. That process of etching away at the protoplanetary disk basically means that anything that doesn't form before that happens will never get enough material to actually accrete a core. A key point in a solar system is at a certain distance from the star, after that ignition of the main sequence starts, there is this point called the snow line. Now, the lightest elements are the ones that are blasted furthest out into the solar system. That's hydrogen, oxygen, chlorites, and that sort of thing. All of the lighter elements that are bound in pairs or on their own, all of those are prone to basically being ejected further out due to the solar wind. Past the snow line, though, it's cold enough for volatile ices to form into structures as hard as rock. That gives things growing past that line a lot more material to actually accrete, which is why every major body in our solar system today, such as the gas giants and the ice giants, all formed past that point. It's the only place where there was enough material for them to actually grow. This runaway growth of outward planets actually creates a bit of an issue, because as a planet's core grows, so does its attraction to the star, and that changes its orbit. As the star grows and the planets grow in this early chaotic period of the solar system, you end up with the largest planets trying to force their way into the inner solar system. In our solar system, this was probably the most notable period of events for defining how our solar system would turn out, and it was called the Grand Tack. So the Grand Tack mainly involved Jupiter. As Jupiter grew, it was so massive it could accrete all of the dust and gas that had been blasted out by the star as it was on its way out into the outer solar system, gaining moons, gaining its massive gaseous atmosphere, and it became what it is today, which has more mass than 2.5 times the rest of the solar system combined, excluding the Sun. This meant that it rapidly moved from the position it formed, which was probably about past Ceres in today's alignment, to overlap with what is now the orbit of Mars. This movement through all of the rock and dust and planetesimals and planetary embryos that was in its way caused absolute chaos for the inner solar system. At this time, the inner solar system wasn't made up of 4 terrestrial planets. It was made up of more likely a few dozen planetary embryos that had just started colliding with each other. But as Jupiter moves in, the effect that it has is essentially lugging all of that asteroid debris and throwing it at the inner solar system. This led to a chain series of impacts which would absolutely define all of the planets, including ours. Once it had moved into about 1.5 astronomical units of the Sun, it then started to retreat. That was because it fell into a 5:2 harmonic ratio of orbits with Saturn as Saturn was growing. This was the reason why Jupiter is in its position now, and this also threw off the balance of Neptune and Uranus. It basically cast all of the heavier planets out into the outer solar system and left the damage that they'd done on the inner solar system. After the grand attack, all that was left was those 4 rocky terrestrial planets, and probably more than half of the mass in the inner solar system would have been either captured or thrown into the sun. Another thing it brought from the outer solar system, which was obviously a key ingredient for Earth that it lacked, was water. So, like I said, water doesn't exist in the inner solar system, not normally anyway. It is blasted out when the sun goes through its main sequence, and at the time that it does, no planet is big enough in the inner solar system to really keep its water. It all gets moved to the outer solar system. When Jupiter moved inwards, however, it basically threw a bunch of water-carrying rocks at Earth, giving Earth, Mars, and Venus all of the water they currently have today. And they did that in the form of rocks such as this. So this is a mineral called chlorite. Now, obviously, normal water would have just evaporated, incinerated, gone into orbit, and then been dragged off. Loads of different things. Could have even been annihilated by solar wind before it even reached Earth. But in this mineral, it's locked up as chlorine and oxygen ions, and then hydrogen that it gained from the outer solar system. These then arrived as meteorites in a period known as the Late Heavy Bombardment, which the grand attack allowed to happen. So this type of rock, along with a few others, is pretty much the reason why Earth actually has water at all. Same goes for Mars or Venus. The effect that Jupiter dragging back out had on Uranus and Neptune was profound, because they both formed a lot closer in, where there was actually material. They're both starved by Jupiter, the same way Saturn was, but they still had enough material to gain many Earth's masses in scale. But then Uranus was ejected to its current position of 19 astronomical units away, and Neptune was cast the furthest out at about 30. This basically doomed them to never have any real interaction with the inner solar system again themselves, but they passed through a dispersed region on the edge of the solar system known as the Kuiper Belt. The Kuiper Belt was much denser at the time that this was happening, and that was where a large proportion of the icy debris and the rocks and stuff that basically comes from exchanging between solar systems, that's where all of it lies. A lot of the moons that not only they picked up, but a lot of the moons that Saturn now has are as a result of debris basically being flung from the outer solar system inwards by Neptune. Now, obviously, it's kind of just a physics equation that if you have more mass in that system, you're going to end up with orbits needing to change. So that's not actually characteristically weird. What makes our solar system so weird is that it went back out again. In a lot of solar systems, this is not the case. In a large number of solar systems, there would be one dominating body that grows by accreting every other planetary core in its region, and then just moves inward and basically annihilates their version of an inner solar system. Take a system like this, WASP-33. Now this is actually to scale, which is kind of scary, and that is not a star that much bigger than the Sun. Now, WASP-33 is an example of a system with what's called a hot Jupiter. Now, hot Jupiters are what would have normally happened with our planet Jupiter had Saturn and the other ice giants not kind of got in the way of that. That one planet has nearly 1.5 times all of the mass of all of the planets in our solar system combined. But at a temperature so extreme that it would rival the surface temperature of some stars, around 3,200 Kelvin. The thing about the WASP-33 system is this is taken to an extreme. A hot Jupiter is defined as having an orbital period of just 10 days or less. This planet has 1.2 days. So pretty much for every Earth day, give or take, this planet has a year around a star a lot hotter than our Sun. So if this was the norm, then our weirdest parts to our solar system have to be the terrestrial worlds. Not entirely. People would look at Earth as the most outlier in the solar system purely because it has life. Geologically, and as a planet, that's not really relevant. Earth as a planet is something that we've seen a lot more commonly than a couple of other members of our local terrestrial neighbourhood. Mercury and our own moon. So both of these have ties to the Grand Tack, both gaining this event about 4.5 billion years ago, pretty much when the solar system was new. These are both prone to what's known as the giant impact hypothesis. For Earth, this entails the young Earth, which had about 0.9 times the mass that it does now, being hit by a Mars-sized planet named Theia. Now, that impact would have been very oblique. It would have basically dislodged large swathes of Earth's crust and the upper mantle and blended it in some way to get very, very, very similar rock contents between the Earth and the Moon when it formed, and basically eject that matter into almost a belt, a bit like Saturn's rings, but a lot thicker, that then clumped up within hours of its impact, forming the Moon. That is where Earth not only gets its very large moon from, but it's also where it gets its axial tilt of 23.5 degrees. And it's also what gives the Moon its velocity away from Earth. So Earth and the Moon's orbits are both slowing due to tidal gravity dragging on each other. But even in spite of that, which is usually quite a balanced system, the Moon is actually moving further away from the Earth because it's still got part of that initial velocity from its impact. The Earth and its Moon are unique in this sense purely because no other terrestrial planet that we know of has a moon as large proportionally as the Earth's. The Earth has a diameter of about 12,000 kilometers, whereas the Moon is about 3,700. That is a size comparison just to show how much bigger that is comparing with, say, Mars and its two very tiny asteroidal moons, or even Jupiter and its massive moons that are tiny in comparison to it. That's something that we can explain. The weirder one, weirdly, is Mercury. Now, Mercury is not something that you commonly look at for being the source of all interest in the solar system. But once you look into its actual structure, how it's made, it becomes a much more interesting story. The Earth's core is also nickel-iron, and it makes up somewhere around between 12-15% the mass of Earth, something like that. Mercury makes up more than 60% of its mass. Now, this suggests that Mercury was on the path to being a significantly larger planet, potentially super-Earth level, but that it got not only stunted in growth, but literally the outside layers of it torn away completely. And if it was on track to become as large as Earth, that could be more than an Earth's worth of debris from that series of impacts. Now, the reason why I say series is because no computer that's tried to model this has been able to do it with one impact. Every single simulation has been based on the presumption that that is the result because we can see it, and then trying to fit some series of improbable events to that. I think some of the simulations have like 7 large impacts at very specific oblique angles, especially as close in as it is to the inside of the solar system. It's just not probable. It's a planet that we can barely model how it actually even got like that in the first place. What we do know is that that series of events would have been responsible for its key characteristic, which is being very, very close to the Sun. It also has a surprisingly elongated orbit compared with some of the more circular orbits of Mars and Venus and Earth. We have never discovered another planet like Mercury. Every other planet in our solar system has an analog somewhere, except for Mercury. Out of 6,000 odd confirmed planets, we know of nothing like it. Uranus is another particularly interesting one that gets overlooked a lot of the time. Now, it doesn't have the extreme deep blues or the storms of Neptune, and it doesn't have the tapestry of Jupiter. It doesn't have the rings of Saturn. But what it does have is an unbelievably weird orbit. So it is the only planet in the solar system that has an axial tilt that is more than 90 degrees. Basically means it's wobbling through space on its side. Compared to the rest of the solar system, that's a very weird thing to do. Now, one of the weirdest things that was found, only one probe has ever been to visit it, by the way, Voyager 2, because it's very, very remote. But when Voyager 2 visited it, one of the things they found really odd was that its north and south poles actually align with its axial tilt. So in this scenario, it wasn't a simple impactor that might have hit it at an oblique angle and rolled it a bit. This was probably the largest impact in the solar system's history, concealed by what looks like quite an ordinary planet. Now, Uranus probably was impacted by a super Earth more than 2 times the mass of Earth, made out of ices. And the fact that it was made out of ices was important in that tipping of the magnetic field as well. This image shows the plasma bursts in Uranus, and alongside that they found traces of high electrostatic field around parts of the clouds in certain belts, indicating that there was debris of ions and charged particles still washing around it, a bit like currents in an ocean. This tied it to a large impactor that would have collided with it and vaporized, ionizing those volatiles, and basically taking the whole magnetic field of the planet with the roll of the planet as well. In doing so, it also created, with part of that, Uranus's largest moon, Titanium. Uranus has a very low density of large moons, just that one. Everything else is smaller, mainly because it was cannibalized by every other planet in the solar system moving about. But that one moon can trace its origins back to potentially the largest impact in the solar system's history. Now, obviously, like I said, Earth as a planet is not necessarily the most unique thing in the world, but that life is something that we can't replicate anywhere else. Earth is the only planet we know to have life. So, life on Earth is a very important thing to look at. Because it's only by looking at life on Earth that we can work out what is the rest of the solar system actually likely to hold. Life on Earth started in deep sea fissure belts. That's widely regarded as probably how it started. Obviously, it's not proven, but it makes sense. Now, an interesting fact about those vents is that they're not permanent. It doesn't create one refuge at the bottom of the sea where bacteria can start a life for infinity and just produce on its own time, they shut down, which means that the immediate advantage of any evolution on Earth to become anything more than just a bacteria would have been to be able to survive between series events as they come on and off. Now, that is something that we see in current deep sea environments today. All of the creatures in that image are crustaceans feeding on the bacteria. Now, those crustaceans share a lineage with shrimp and squat lobsters that you find elsewhere, but crucially, they're adapted for just that environment. If that shut down, all of the bacteria in that colony would die off. But the creatures, and then by proxy, any bacteria that can hold on to that as well, may survive by keep transferring to the next deep sea vent. If they don't find another vent, they will die. There's no real other source of food for that type of organism. The problem is, it is an extreme environment to change from. You're talking temperatures that would melt lead and very, very, very high sulfur content. It's not something that is easy to go from that to just eating a fish. The next thing that we focus on with evolution is that it's misunderstood by a lot of people how evolution actually moves forwards. People like to think of that image called the March of Progress. Now, that's not remotely how evolution works. Evolution is not a progressional thing. It's random, and if a trait is wanted in its environment, it's likely to be reproduced into the next generation. That's evolution. There's no guarantee of becoming human eventually, for example. And a good example of this is early tetrapods. So the earliest things to come onto land are now actually believed to have not developed that for coming onto land. They developed it to just gain environments where there were less fish, or more to hunt, but less that they can hunt them. And their environments resembled wetlands of broken up streams, lakes. Their tetrapod-like bodies were literally just to drag themselves across the brief bit of mud between their first pond and their second pond. An adaptation that we now take for granted of life was destined to try and get onto land had nothing to do with getting onto land specifically. It just had more to do with a random thing that benefited a fish when it tried to go to the next pool along. The overlying fact, though, is that nothing on Earth is really possible without cycles such as this. So Earth is actually quite unique for having plate tectonics. Plate tectonics are a way of either oceanic or continental crust moving about on the surface of the planet and meeting at different boundaries. It basically takes heavier, more dense oceanic crust and drags that into the mantle under the continental crust, which is lighter. As rain weathers the land, it puts carbon into the sea. That carbon works its way through food chains, it works its way through mineral webs, and eventually ends up at the bottom of the sea. When that plate then goes under the continental crust and melts, it then gets released in volcanoes. It's the key basis of the carbon cycle, and it monitors temperature across the planet. If one thing changes, pretty much another thing will change to balance it. Unless you have an extinction event, which does happen occasionally. But for the most part, it does actually keep the planet in check. Now, this, I believe personally, is something that it is almost impossible to create a stable environment without. So, in looking for a planet that is habitable, you might have to look for one where you have to be living next to an active volcano or in a fault boundary. Now, life on Earth also reached extremes due to these kind of changes eventually. Some of these I mentioned before, but I just thought I'd bring them up again. That could be extremes of size, extremes of adaptations for existing in very harsh environments, or extremes of becoming unlike any other form of life on Earth, such as very different variants of extremophile bacteria. Now, Earth has the niches for life to exist easily now, or relatively easily, and yet life still pushes everything to the limit all the time. That gives us something to try and understand the rest of the universe by, but it also throws big questions at us like, how do they actually do it? But it does seem, given that initial evolution at that one spot in those vents, life will try and conquer every niche as long as there is one, no matter how stupid or extreme or how much we can't understand how that works. In the wise words of someone, life finds a way. So, moving that on to other planets. Our solar system was also quite unique because it didn't just have one terrestrial world that could bear water. It actually had 3. So, obviously, a lot of people know about Mars having oceans. It's a very well documented thing, and we've got rovers there right now looking through old riverbeds and lakes and structures that are undeniably free of water. But the interesting thing that's less known is Venus, Earth's twin, is also started out in life as a watery world. The interesting difference, though, is Mars, despite everyone liking to think it was a place that potentially could hold life, it was nothing like Earth. It had much, much less mass. It is about half the width. Venus is much more an Earth analogue. Due to its tiny size and its low mass, Mars probably only had its water for around 500 million years. It meant that it was long enough for it to carve some of the extreme geologic formations we see there today, but probably not long enough to even start thinking about microbes being a possibility. Venus, on the other hand, was for a very long time the most habitable planet in our solar system. When Venus was habitable, the Sun was about 80% the luminosity that it is now. So Venus fell more easily into that habitable zone than Earth did at the time. Venus also had 2 billion years of water on its surface, nearly half the solar system's history. Venus wasn't hell. Now, life on Earth was expected to have formed within the first billion years. So, chances of life ever having been on Mars, low. But the chances of life potentially developing on Venus is very high. Despite Venus's similarities to Earth, though, it today doesn't resemble Earth in any way. It is surprisingly the hottest planet in the solar system. It has surface temperatures that peak at around 470-ish degrees, hot enough to melt lead, and very high acidity and surface pressures of around about 100 times Earth's atmosphere. It's sort of analogous to going into a boiling ocean 400 or so meters deep. That means that anything that did evolve there has a very, very hard chance of ever existing there now. And we also struggled to get there. There was a Soviet lander that managed to last something like between 20 or 40 minutes on its surface called Venera 9. And pretty much that's the best data we have about the surface of Venus even today. But there are ideas of how life could have adapted to that situation by using that heavy air column, by essentially suspending themselves in the mineral bands of its mid to upper atmosphere, where temperatures are very analogous to Earth's. And the same things that make Venus's atmosphere so toxic to us have a striking resemblance to the minerals that you find in the deep sea vents, the sulfides and that sort of thing, that bacteria is known to fix on Earth to create energy. Moon systems allow these kind of microcosms of life to pop up all over the solar system, purely because they're piggybacking off planets that are so massive that you can generate heat by proxy. Now, that is the nice image of Jupiter and its major moons, just to show the diversity of things that were picked up in the early solar system. That is the collection of all of Jupiter's known moons. Most of them are very small, other than obviously the major ones, though some of them are still a couple of 100 meters wide to a kilometer or so. Jupiter, Saturn, and Uranus, and then Neptune later on, pretty much hoovered up the remnants of what would have made massive asteroid belts. The process that moons get heated by a large partner it's called tidal heating, and basically it frictionally heats the inside of a moon, so even a very small body that would never generate enough heat on its own can actually have that same source of geothermal heat that Earth can replicate on seafloor or near a volcano or whatever. A good example of this is Jupiter's closest moon, Io. That is the most volcanically active place in the solar system. It also has the largest volcano. The volcano on Io, obviously it has much lower gravity, but the supervolcano it holds has been known to erupt very frequently, a couple of times every 100 days, and blast magma and ejecta and ash 300 kilometers into the sky. Now, on a moon that is, still relatively small, that is about a tenth the width of Io. So that force is unbelievable to actually create an analogue of someone like Venus or Mars in such a very small body orbiting such a big gas giant. Another thing that these moon systems benefit from their donors, especially when they are a gas giant, is they can piggyback on the magnetic field. So the magnetic field was one of the reasons why Mars had its downfall. The core froze purely because there wasn't enough mass to keep it warm. When the core froze, there was no longer magma and iron churning around inside the planet generating its magnetic field, which meant it was open to the sun's bombardment of solar rays. That slowly strips away the atmosphere and took all chances of life away, also stripping it of water in the exact same way that it stripped the inner solar system at the time of its birth. This doesn't happen on these kind of worlds, partly because they don't have much to strip away in the first place, but also because the gas giants' magnetic fields are so strong. I think Jupiter's is around 1,000 or 2,000 times stronger than Earth's, that they basically engulf the whole inner moon system, exactly like the sun does with our entire solar system. It is like a microcosm of a solar system within a solar system. A very good example of how extreme this can be is Saturn's moon, Enceladus. So Enceladus is very well known to have a tidally heated ocean and is known for its immense geysers on its southern pole. Now, Enceladus is properly tiny. It's about the length of the UK. It is very small. It is comedically small. You would stand on the surface and literally see the curvature very clearly. But even that has been proven to have some solid inner structure that is being tidally heated, and the vast majority of its volume taken up by an internal ocean. That means that, technically speaking, Enceladus might be able to mimic Earth's early life, despite having no mass at all. If that was on its own in the middle of the asteroid belt or something like that, it would have no chance of being anything other than a tiny little ball of ice. Its proximity to Saturn is actually the key to its success. It orbits within the bounds just of Saturn's rings. That is very, very near the point where an object would begin to break up due to its gravity. If it was any larger, it would be disintegrated just the same way the bodies that made up the rings in the first place were. it being tiny has allowed a very unique little system to develop around the rings. Much larger scale of that, with the same premise, is the more famous moon Europa. Now, Europa is actually big. It's some 3,000 or 4,000 kilometers wide. That makes it one of the largest moons in our solar system, and the tidal heating is also very prevalent for that. It is the most notable source for a subsurface ocean, probably the largest subsurface ocean in the solar system. And all of the cracks on the surface are created by that water moving about underneath in currents and belts and tidal streams, just like a water world would, but coated over with a layer of ice. Interestingly, Earth was once frozen over as well, and potentially the way that life survives on Europa might mimic the way that life survived on Earth during that time as well. Another notable contender is the immense moon of Ganymede. So Ganymede is the largest moon in the solar system, with a diameter of over 5,200 kilometers, nearly half the size of Earth, and yet it's just a moon. Now, it has a frozen crust, and it's filled to pockets of subsurface ocean, but the most notable thing about it is the chemical lakes underneath it that are heated in the same way. It probably doesn't have as much chance of life as Europa or maybe even Enceladus, but it's an interesting contender purely because of its insane size. The probably most unique moon in our entire solar system, though, doesn't orbit Jupiter, it orbits Saturn. That is a planet for a moon. Titan is the only object, the only moon we know of that has an atmosphere, permanent atmosphere, and it's a thick atmosphere as well. It also has a particularly interesting feature, which is that it has surface lakes of liquid methane. Its temperature hovers around 100 Kelvin, so about minus 170 degrees, which obviously methane on Earth is a gas. But on Titan, it has the right temperature and the right pressure of its atmosphere to generate a methane cycle, very analogous to Earth's water cycle. That means at the poles, you have frozen methane tundra and methane ice caps. You then have lakes and rivers of methane running through systems that carve in the same way that you would on Mars. Then you have evaporation from daytime, nighttime cycles, the same as you would on Earth, creating upwellings of vaporous methane that then passes over solid ice mountains and then falls as rain, but methane rain. Its striking similarity to Earth's cycle is an intriguing thing because potentially, if life couldn't adapt to the conditions or the actual solution of that chemical soup, then it could be completely barren. But if life did evolve in that sense, in some way that we're not quite familiar with, at least not on Earth, then it could have striking resemblance to Earth, but in a completely alien environment. Another interesting contender for the weird moons is Triton. So Triton is Neptune's largest moon, and it's the coldest object in the solar system. It has temperatures that hover around 38 Kelvin, very close to absolute zero. Yet even out as far as this, due to its very odd orbit, it is one of the few, well, it's the only large moon in the solar system that actually orbits in the other way to its planetary host. So Neptune spins in the same way that every planet in the solar system spins other than Venus. But Triton is presumed to have been captured either from a nearby collision event or it forming somewhere in the Kuiper Belt and Neptune migrating past it, capturing it in that way. But what it means is that it has an amplified amount of tidal heating. As it tries to spin, Neptune tries to stabilize it in the same way that the solar system tries to flatten everything else out into a plane. And this battle between the two momentums creates enough heating to get geysers on the coldest object in the solar system. Potentially, there is a means of life even as far out and as on a desolate body as Triton is. If that's true, then it's possible companions between large enough bodies or enough of them could survive much further out from a star than we ever thought was possible to actually create life. Despite the intrigue of Triton, there's actually quite little known about how these geysers work with its internal system. It has quite a thick crust, and a lot of its secrets are still shrouded away. Plus, only one spacecraft has ever visited it, and that's probably not going to change anytime soon. Despite that, it will probably be something to study from afar with our new space telescopes, just to see if we can make out something about it. But there is obviously a more distant object in the solar system, a few, but one in particular. Pluto has a very interesting relationship with its closest moon. Weirdly enough, Pluto actually has more moons than any terrestrial body on the inner solar system. It actually has 5 moons. 4 of them are very small, but one of them is unique for having the largest size compared with its orbital body of anything in the solar system. So Pluto is around 2,300, 2,400 kilometers wide. Charon is about 1,300 kilometers wide. But crucially, it's about an eighth the mass. Now, the Moon to Earth mass ratio is about 1 to 80. The fact that these are so close and have such similar masses comparatively means that the system's barycenter, the actual center of where the two objects orbit, is outside of the surface of Pluto. It actually makes people think that this is more like a dwarf planet binary system than a moon system. Either way, the effect it has is incredible, because when people were looking into Pluto with the New Horizons spacecraft, they didn't really expect to find much beyond a frozen object that could tell them secrets about the very birth of the solar system. What they did find, in fact, though, was still evidence of the subsurface ocean due to its companion, nothing else. It's the only form of this extreme tidal heating that isn't linked to a gas giant. And a very good example of how that happens is a region that's often known as the White Heart. Now, that is a massive cold trap. It's something that was carved out by a massive impactor and allowed Pluto's extremely cold nitrogen atmosphere to basically flood in and lowered the temperature to the point where it formed this crust of nitrogen solid ice. Below that, however, the surface of what would have been the surface of the planet gets incubated, and that, in combination with the binary orbit, can generate just about enough energy once it's mixed with the other chemicals there to potentially melt the surface of the ice. The channels that you see in and around the Tombaugh region is not conclusive proof, but it does show that there's some upwelling and downwelling. It's basically suggesting that even in a situation as remote as this, without even a host gas giant, there is a chance that something could be there. A very interesting thing that it found out as it was passing away, though, is Pluto's atmosphere. Despite being tiny in mass, obviously not even big enough to be a planet, Pluto actually does have what's called a transient atmosphere. Transient means that it's only active when the sun is actually on it. So as this very odd system of a cycle to reuse and replane the nitrogen ice by literally vaporizing it in the day, taking it around the sides of the planet where it cools and then falls as ice-like rain. This is complex systems existing on a body that isn't at all complex, or shouldn't be. All of this, again, is pretty much driven by either the chemical composition of bodies that are so far flung in the solar system, or simply having a partner there. These sort of binary relationships are something that we really want to look for when we're looking at other solar systems. The issue is, it took us until a couple of decades before New Horizons even went to see Pluto to even figure out anything about its moons at all. Trying to spot an object even within the solar system that small with a counterpart that's that close and even smaller, it's basically impossible. Though more recently, we've been able to take pictures of the insides of other solar systems, something I thought would be science fiction forever. Instead of just feeling what's going on there by sensing if there's a slight change in a star's output or if there's a gravitational wobble in its light, we now have the capability to actually image planets in other solar systems. So potentially with that level of accuracy, one day we might be able to find moons and systems that look analogous to ones that we see in our solar system to think about studying further and see if we could find any sources of life. It is quite probable that gas giants will share these same traits everywhere in the solar system, everywhere in the universe. But until we prove it, anything could be true. So, from the first collisions and the now dead planets of Mars and Venus to the icy reaches of the very outer solar system, every single object pretty much in our solar system has shown a layer of depth to it that we wouldn't have ever believed. Everything that we feel as normal, everything we look at as dead or unimportant, has shown up secrets that we can translate to everything else we see. The only thing left to do is, as technology advances, we'll be able to travel out further, we'll have to study more in person, we'll be able to actually verify if all of these signs where I'm saying about subsurface oceans or geysers or all of that, we'll be able to go there and actually have a look for the first time ever. And it will be interesting to see what's out there. Questions?
Do you think there was life on Venus at the same time?
I reckon there was. The thing is, Earth obviously had the massive impact that formed the moon. So that was around about the beginning of the solar system. It was about 100 or so million years after. But that was still 100 million years. Then the planet had to reform its surface and reshift everything about it and form a tandem with this massive co-partner. So I reckon that potentially delayed life on Earth, at least for that time. So Venus might have even beaten Earth to the punch on life, but without the same level of complexity of tectonics or without the same large moon to actually balance out the system. I don't believe that even if Venus still had water on it, life would have ever managed to reach the same complexities that it has on Earth.
When you're talking about Mercury, about how unusual that is, with its so-called close to the sun that has such a major, huge core, right? If we wanted to find another planet that's similar to that, like how would we really search for them?
So the thing that we're looking for is essentially density. So because the core is always going to be the densest part. Now, everything that makes up the outside layers is mainly of terrestrial planets is mainly silicate rock and that sort of thing, lighter elements, and then in some weird cases you find places richer in even lighter metals like lithium and beryllium. To find a planet in a near circular orbit, you can sort of estimate its mass purely because of working in its orbital speed and distance and the relationship it has with other things in its group. So the same way that I could say about the mass of that planet, we could define the mass of a planet like that and basically calculate the density. So the density of Mercury is higher than the density of any other terrestrial world we've ever found, purely because 60% of it is that iron nickel core.
Go further on that. I think finding another planet like Mercury in particular, but also just other observations, is that do we think that our solar system is quite strange and unique because we can see it better because we're inside it? Is it not that we can't verify that exoplanets solar systems are as crazy because the observation techniques are different?
That is obviously a point. So one thing that was so going back to this, hot Jupiters for a while were thought to be the only other planet in the universe. So pretty much the earliest planets, other than the first one being a weird fluke of someone looking for something with a pulsar, but after that, it was pretty much every single planet that was turning up by mainly transit method was one of these hot Jupiters, purely because the orbital period is every 10 days or less. So you would see repeatedly this dim, then this dim on the same period, then this dim again, same period. Okay, then there's something there. Find out what size it is, and it blocks out a large portion of the light due to its proximity. So there's always going to be a massive bias for this. But the thing that we can then trace back from there and try and erase the bias is the fact that that one planet has more than 1.4 times the mass of all of the planets in our solar system combined. And it's so close in and would not have formed there that you can guarantee that it's ploughed through that inner solar system region, and that if there is anything left there, it's probably not going to be on the order of stable or, it's probably not really noticeable. It's probably eaten all of it. But outer solar system stuff, yeah, we have no real idea. There could be a lot of things out there, but the collisions and that sort of bit that happen with Mercury is something that is much more characteristic of the inner solar system because of that sort of thing.
Right, I see. Speaking of the outer solar system, I did want to ask, you got any thoughts of the Planet 9 theory?
Yes, so I believe it is there. It's an absolutely beautiful piece of evidence. So I don't know whether did I show this up on the actual a bit, right. So you see how there's this sporadic outer reach of the dwarf planets. Everything in past a certain point is orbiting quite neatly. That's kind of a bit of a weird thing, but it's like, yeah, it's more tight to the sun. The moment you go past a certain point, though, the Sednoids, which are all of the really distant ones, including Eris and several other ones beyond the Kuiper Belt that we've detected, they all have very looping, elongated orbits. That's not surprising because they're coming from further out and they're basically looping in a bit like a long period comet. What is surprising is all of them loop in from the same side, give or take one or two that have really strange orbits. This points to some gravitational counterbalance. Now, in I think the first one of these that I did, I talked about the idea of a system is easy to simulate using a point mass. Now, at a large enough distance, which Planet 9 very much is, you can basically say that the mass in this area is roughly even. The mass beyond that, where it gets more sporadic, is much lower density, much less even. So the gravitational trail that you leave is only noticeable on the longest of scales, purely because the gravity is focused in the middle. So that trail of the Sednoids and transneptunian objects coming in from the same side suggests that there's a gravitational counterbalance far enough away that you can assume the middle of the solar system as essentially a point mass. That puts it as an estimate of, I think it's currently sitting around 5 to 10 times the Earth's mass. Basically, it's an ice giant sort of size planet.
Why haven't we seen it? What would be the reason we haven't spotted it?
Because it's basically, I mean, you're talking about spotting the planets in other solar systems. They are specifically ones very close to the sun that are reflecting a lot of light. Now, Planet 9 is quite big, but it's not big compared with anything else. And the amount of light it's reflecting is absolutely tiny because it's so far out. Basically, what you're looking for is a pinprick on less than a pinprick to cover a star and still not say that that's a random event of some other tiny object getting in the way before that. It's going to be a dark colour because it's a gas giant. It's not reflective like ice. It's going to be very nearly impossible unless we can pick up what position it's going to be in and then focus every camera we have on a star that is in the path. If it crosses that exact time we calculate, that'll be the proof.
Okay. Just don't have that all, but yeah.
Yeah, no, we don't. I think they've got a trace in the sky of where they think, but the orbital period is so long, it's something like 20 or 40 or 1,000 years, depending on the distance. So, there's not enough data to get an entire orbital path within even since the ancient Egyptians. I mean, it's mad. It might have crossed that much of the sky since we've had the ability to even search for stuff.
There is still remain search and trying to find it.
So there was a specific group of people who put them aside. I can't remember exactly what organisation they were from. I think they were part of ESA, but they saw. So it was one of them who proposed the counterbalance theory, and it was a separate team that was trying to define a different Planet 9 in tandem with that, which gave this one the name Planet X. So that was a Mars-sized body that's since been disproved because it didn't need to be there. The team is quite small that's been extensively doing this. It's something like 10 or so people, but they've had a lot of stuff published more recently. I can't remember the exact names, but if you look up about Planet 9 research, they will come up.
Something about Uranus you mentioned is how its axis of rotation is tilted.
Yeah.
Why exactly is that unusual?
Because Uranus is still quite massive. I don't know exactly how massive it is. I can't remember. I think it's about 9 solar masses. No, 9 solar masses. Nine Earth masses. Yeah, it's a Class A star. About 9 Earth masses or something like that. So to tip something of that mass, a head-on collision wouldn't have tipped it. That's kind of why it's an abnormal thing. So, for example, Venus is only tipped by a tiny bit, but it rotates backwards just because of how that impact hit it. It basically stopped it in its tracks. Head-on collisions are of stuff that forms within the disk and then just collides due to their gravity aligning them. Chaotic impacts are common in the inner solar system because there's so many objects. For a planet of that mass to hit at the right place to tip a gas giant in the outer solar system makes it a very rare event. So Neptune, I think, has a 26-degree tilt due to a set of interactions and basically engulfing some of the stuff to grow in mass. But still, nothing compared with that. That would have been one major impact.
Yeah, but like a 0-degree tilt, right? So perfect kind of alignment would be considered normal.
I mean, it wouldn't be necessarily considered normal because that would have meant it wouldn't have interacted with anything.
Well, do they sort of tend to be in that sort of range, being closer?
I would say kind of 0 to 10 degrees is kind of that's just normal levels of things colliding. Anything beyond that is something's been prevalent from one side, at least.
What was like the physical reason for it to be aligned that way?
So Uranus's tilt was because the planet hitting it would have hit at an oblique, either upper angle or something like that. It would have been enough to basically frictionally grab the core of the planet and just turn it. and then the ices that actually got vaporized in that are then ionized, so that then drags around the magnetic field and whatever, so it's not resisting on itself, which is why it's allowed to stay in that orbit. But interestingly, because of how its gravity worked since, and because it picked up a lot of debris from that, its entire moon system is on its plane. So its entire moon system is at 98 degrees to the plane of the solar system, which is odd because it means that the moons are rotating like this, but it's only the pole given a certain period of time. One pole is entirely sun, and then the other half of the planet is entirely dark because it's moving sort of like that against the sun.
Another thing we mentioned, I think, in the very first lecture about how when you have a bunch of things rotating around planets or a star or stuff around the center of the galaxy, it tends to flatten out.
Yes.
Eventually. When we looked at Jupiter's moons, the little diagram we showed earlier.
That was because of what we were talking about with satellites, where they're very low mass.
Yeah.
So that just has an impact on how much they're affected by that. Essentially,
but they do have that effect. Sort of.
They have that effect. There is actually a trend to it. If you look at it, it's just because it's actually where was it?
Yeah.
There is a. It's what we call a torus shape for the most part. So there's the sphere on the outside. Everything within a certain distance basically flattens out to torus, like a donut.
Mm-hmm.
So it's not flattened out into a disk, but it's sort of somewhere between flattening. It's gaining the same gravitational influence.
Okay.
But because they're a bunch of long period things and whatever, and they don't have much mass, they don't have anywhere near the same gravitational force, and they're mainly just attracted to Jupiter anyway. Obviously, for a low mass thing, the speed that it needs to be orbiting is much less for the Sun than it is for Jupiter itself. Plus, Jupiter, I'm not 100% sure about this at that distance because I don't think it will have an effect. But because they're small, potentially Jupiter's magnetic field would have an effect on that as well. Because a lot of that will be iron-rich rock and that sort of thing. And obviously ice. Adam? Okay, cool.